Hello viewers, welcome to Add-on. In this question, we are asked, explain transistor as an amplifier, as an switch. Okay, so we need to describe the working of a transistor as an amplifier as well as a switch. So let us first start by explaining the use of transistor as an amplifier. Okay, so this amplifier This amplifier helps in the amplification process. Now, what is amplification process? Amplification process is the phenomenon in which the magnitude of the input signal gets boosted or gets increased at the output. For example, at the input side, we are giving a 5-volt signal. Okay. The signal has a peak magnitude of 5 volt. Okay. And at the output side, we are getting a signal which has a peak amplitude of 50 volt. So, what is the gain here? 50 by 5, which is equals to 10. So, the input signal is amplified by a factor of 10 when we are using a amplifier. Okay. So, here we are asked how we can configure this transistor as an amplifier. Okay. So first of all, we need to know that the transistor operates in three regions. One is the active region, one is the saturation region, and another is the cutoff region. Okay. So the transistor only operates as an amplifier in the active region. And what happens in the active region? The emitter base junction is forward biased and the collector base junction is reverse biased. Okay. So we need to maintain these two categories or two biasing to make sure that our transistor always operates in a active region. So when the transistor is operating in an active region, the transistor will act as an amplifier. And the next step will be, this was the first step, which was choosing the mode of the operation. Okay. And the next step will be choosing the transistor configuration. Now transistor configuration are three types: CE, CB, and CT. Common emitter, common base, and common collector. Now, when the transistor is operating in an active mode, the transistor will work as an amplifier. But choosing this three configuration will help us determine how much the amplification will occur. For example, this 5-volt signal is amplified by a factor of 10. Okay. So, for example, I am assuming that this 10 amplification is occurring in CE mode. Okay. But it may arise that in the CB mode, the amplification factor will reduce to a factor of suppose 8. So, then the input signal of 5 volt will amplify to 48 volt. Sorry, 40 volt. Okay. 40 volt. And suppose in the common collector configuration, the amplification factor is reduced from 10 to 9. So the output voltage becomes 45 volt. So we can see that the signal 5 volt is amplified in all of these three cases. But the magnitude of amplification is different in all of these three. Okay. And this magnitude of amplification depends on the configuration of the transistor, whether it is in CE mode, whether it is in CB mode, or whether it is in CC mode. Okay. So here I have made the assumption following the condition that in CE mode, the gain of the amplifier is highest. In the CC mode, the gain of the amplifier is moderate. And in the CB mode, the gain of the amplifier is lowest. Okay. So for our convenience, we will choose the CE mode of configuration because in the CE mode, the transistor will give us a faithful gain at the output. Okay. And we know in CE mode, the current amplification factor is given by beta, which is equal to IC divided by IB. Okay. So this is the collector current, this is the base current, and this is the current amplification factor. And this current amplification factor varies from 50 to 200. Okay. So this will give us a faithful amplification. Now, in order to ensure that this transistor operating in a CE mode will give us a faithful amplification at the output each and every single time, we need to do the biasing. Because if we don't give the biasing, what happens? That when the temperature changes, like the transistor Suppose the transistor is at T is equal to 20 degrees centigrade. So at that time, the transistor is giving a amplification of factor 50. But when the temperature changes from 20 degrees centigrade to 25 degrees centigrade, then the amplification factor will reduce to say 30. Okay. So as the temperature is changing, even with the same configuration of the amplifier and in the same mode of operation of the amplifier or transistor, the amplification factor is reducing from 50 to 30. Okay. This is due to this external temperature condition. So in order to make sure that even if the temperature changes, the amplifier doesn't change its amplification factor, we need to give it the biasing. Okay. So we will draw the circuit diagram of the amplifier or the circuit diagram of the transistor as an amplifier. So as I have said, we need to follow true criteria. This is the mode of operation should be active and the transistor configuration should be in C mode. And we will give the biasing accordingly. Okay. So let us draw the circuit diagram. So this is the total circuit. This is the base terminal. This is the collector terminal and this is the emitter terminal. Okay. So this is the input source. We are naming it as V of S, which signifies that this is the voltage source. This is the blocking capacitor. Okay. So the principal function of this blocking capacitor is to reject all the DC components of this input AC signal. Okay. So this blocking capacitor will reject all the DC components of the input AC signal, and it will also couple this input AC signal to the input side of the transistor. And this is the voltage divider biasing we have used here. This is R1, this is R2. This is the voltage divider biasing. We also could have used bias or cell bias, but we have used voltage divider bias because the stability factor, which is S, okay, the stability factor, which is S, is lowest for the voltage divider biasing. So the stability of this biasing is highest. Okay. So we have used here the voltage divider biasing. This is the collector resistance RC. This is the emitter resistance RE. This is the bypass capacitor C of E. This bypasses the emitter current to the ground, because if the current which is passing through the emitter is not bypassed to the ground, what happens is the voltage gain will reduce. So in order to increase the voltage gain, this emitter capacitance will bypass the emitter current to the ground. And this is the coupling capacitor. This will couple the output to the load resistance. Okay. And across this load resistance, we will measure the V output or the output voltage. Okay. And one thing we need to make sure that here we will apply our supply voltage, which is VCC, which can be taken as 15 volt. Okay. So here the current will be flowing as IE. Here the current will be flowing as IC. Okay. So this is the, we can say, the main circuit diagram of a C transistor as an amplifier. Okay. So this is the main circuit diagram of it. But one thing we need to make sure in this is that this V output, this is the output voltage. If we apply KVL in this direction, this V output will give us VCC minus ICRC. Okay. V output is equal to VCC minus ICRC. So if we find the voltage gain of this C amplifier, we can do it by any kind of model, hybrid pi or any kind of hybrid pi, or you can use hybrid model as well. So if we find the voltage gain of this amplifier without using any kind of model, we can also give it as A of V. This is the voltage gain. This is equals to V output divided by V input. Okay. So this V output is equals to IC into RC. Okay. This V output is equal to IC into RC, but there will be a minus sign at the first. Okay. Is equal to V output is equal to IC into RC, which is negative. Okay. And the V input is equals to this current here flowing is IB, and this R1 and R2, this R1 and R2 form a parallel combination to get us the base resistance. Okay. So this R1 and R2 will form a parallel combination to give us RB, and so the input voltage will be IB into RB. Okay. So this is the voltage gain. So we know IC by IB, this is the beta factor. So we are representing as beta of AC divided by RC by RB. Now the question arises, how this minus sign come here. So we can see here this V output is equals to VCC minus ICRC. Okay. But if we write the change of output voltage, which is denoted by del of V out, this is the change in the output voltage. It will represent it as del of VCC. But the thing is, del of VCC is not true. This is not true because the VCC is a fixed voltage power. This is a fixed voltage supply, which is in most of the cases is equal to 15 volt. So this VCC is not changing at all. The VCC is always fixed. Okay, so if we are finding out the del of V out, the VCC will be equal to 0, del of VCC. And here in ICRC, the collector resistance, the resistance value is always fixed. We cannot vary the value of the resistance. Okay, so the resistance value will remain fixed always, and the collector current, this will vary. Okay, so we can represent del of V out is equal to 0 minus RC del of IC. So it can be represented as RC del of IC. So if we find the, here I am showing, if we find the voltage gain as a change in output voltage and input voltage, we can write it as minus IC del of IC divided by RB del of IB. Because this IB and IC can change because they are the current, and by using the biasing condition, this value can be changed, and the RC and RB, these are the fixed values. Okay. So this will give us minus beta of AC, IC del of IC divided by del of IB. And this minus sign signifies that the output will be out of phase. Okay. This is one important thing that we need to know. The output will be out of phase. Like for example, let me clear some space here. So if the input voltage that we are applying here, suppose this is the input voltage, one sec. Suppose this is the input voltage that we are applying here. This is like this. Then the output voltage, which will be an amplified version of this, it will be like this. So we can see the magnitude is amplified, but the signal is out of phase because the minus sign signifies that there is a 180-degree phase shift. Okay. So this is the working of a transistor as an amplifier. Next, we will discuss about the working of a transistor as a switch. So in working of an amplifier as a switch, as I have discussed earlier, there are basically three modes of operation, which are active, saturation, and cutoff. So the operation of transistor as an amplifier is in the active mode of operation. But when we want to use the amplifier, or sorry, if we want to use the transistor as a switch, okay, we need to use the mode of operation, which is the cutoff mode of operation. So this cutoff mode of operation is used for using the transistor as a switch. Okay. So the thing is, what happens in the cutoff region? So during the cutoff region, the current does not flow through the transistor. Okay. The base current, that is IB, the base current which is IB, it will equal to 0. So the change in the collector current, it will be also equal to 0. Okay. As in both cases, the current value is 0, right? The value of the voltage of the collector, which is V of CE, this is the voltage at the collector, it will be maximum. Okay, it will be maximum. So as this value increases, the region of the depletion or the depletion layer will increase. Okay, so this is the main principle of the transistor is a switch. Okay, so if you want to draw the circuit diagram of a transistor as a switch, it will be like this. Okay, so this is the circuit diagram. This is the input voltage that we are applying here. This is a kind of variable voltage. This is the base resistance. This is the base terminal. This is the collector terminal. This is the emitter terminal. This is the emitter current which is flowing here. This is the collector resistance. This is another variable voltage. And this is the output voltage. Okay, V of output, and this is the V of input. Okay, so when the transistor is used as a switch, there are basically two operating regions. Okay, so one region I have explained here, which is the cutoff region. Okay, so during this cutoff region, this transistor will operate as a switch, but it will be acting as a off, because during this time the current passing through the transistor will be equal to 0. Okay, and now as we know that in a switch there are two mode of operation, on or off. So during the cutoff mode of operation, the transistor is using as a off mode of switch. So in order to use the on mode of switch, we need to use the saturation mode. Now in the saturation mode, what happens? In the saturation mode, both the emitter based junction and the collector based junction, they both are forward biased. Okay, they both are forward biased. But in the cutoff region, the emitter based junction was reverse biased and the collector based junction was also reverse biased. So as the reverse biasing was that much high, the region of depletion was very much high. So the electrons can pass to the emitter to the collector. So for this reason, the current will be almost equal to 0 during the cutoff mode of operation. So during that time, the transistor will act as an off switch. But during the saturation mode, both of these junctions are forward bias. So what happens during forward bias? The base current IB, which is applied to the transistor, is maximum. And due to this reason, the maximum current is obtained at the collector region. And since the current obtained is maximum, the voltage at the collector will be minimum. In this case, the voltage at the collector was maximum, but during this case, the voltage of the collector will be minimum. So as the voltage at the collector is minimum, the transistor is said to be in full on mode of operation. Okay. So this is the application of transistor as a switch. So one thing we need to know, in the active region, it will operate as an amplifier. The transistor will operate as an amplifier. And in saturation mode or in cutoff mode, the transistor will operate as an switch. Okay. In saturation mode, it will be on. In the cutoff mode, it will be off. In the cutoff mode, there will be no current passing through the transistor because all the junction are reverse biased. And as we know, in a PN junction, when it is reverse biased, the depletion region will increase and no electron will pass from the one side of the junction to the other side of the junction. So during the cutoff mode, the current will be 0. So the transistor will be off, and during saturation mode, both of the junction are forward biased. And as we know, when the PN junction is forward biased, the depletion will decreases and electrons easily pass from one side of junction to other side of junction. So the current will be maximum in the saturation mode. So during this time, the transistor will be in on mode. So this is the operation of transistor as an amplifier and switch. Thank you.